So far in this course, we've concentrated on matrices as algebraic entities, and we've done quite a lot of work looking at their algebraic properties. But matrices have also very useful and interesting geometric interpretations, and we are going to look at matrices now from that point of view and show how an interesting geometric property of matrices ties in very closely with the algebraic eigenvalue problem. If we take the coordinate 3, 1 of the endpoint of this vector and operate on them with this matrix, we get 11, 7, the endpoint of this second vector. Now, what can we say about the geometry of this? Well, clearly, our vector has changed its direction in an anti-clockwise sense, and it's changed its size too. For the moment, ignore the size. Let's see what the same matrix does to another vector. This vector moves clockwise. How about this one? Well, that moves clockwise too, but only a little. You could guess that in this area we could find a vector that didn't change direction at all. Let's look for it. We'll sweep this vector around like this and get the computer to plot the result of operating on the vector with the matrix. We're looking for a vector that doesn't change direction. For this particular matrix, there's a special direction, and every vector in this direction goes to another vector in the same direction. Out here, the vectors seem to be pulled anti-clockwise in towards this special direction, and that's true over here, where they're pulled clockwise. Well, the pull will be strong enough right around here. Well, it's pulled to the same line, but in the opposite direction. For any vector in that direction, no matter what its size, the result lies in the same direction. Well, what do we see there? We saw, as you already know, that matrices move vectors around. If you operate on a vector with a matrix, you get another vector. And you can think of that geometrically as vectors being transformed to other vectors by matrices. But there's something else we saw there, something new. Certainly for this matrix, some vectors don't have their directions changed. For this particular matrix, there's a special direction, and every vector in this direction goes to another vector in the same direction. Of course, its size is changed, but its direction is unchanged. Well, was there something special about this matrix that we used? Will that happen for any matrix? Let's have a look. We'll use this matrix and see what it does to a vector in the same direction as before. Well, its direction changes, so if there is a special direction, it's not the same as for the matrix we had before. But we can hunt in the same way. And this direction has the property that we're looking for, and we'd expect the opposite direction to have it too. And it does. Can we always find a special direction? Look at this matrix. Now, this is different behavior. Every vector is moved anti-clockwise, and there's no special direction. So it's certainly not the case that every matrix has a special direction. And it's fairly obvious in this case, why not? This is just a multiple of a rotation matrix. And so every vector gets rotated through an angle of 45 degrees. So you're never going to get a vector whose direction doesn't change. But the one that we saw at the beginning of the program clearly wasn't a fluke, because we've seen other matrices, like this one, that do have special directions. Obviously, for the moment, we're most interested in those that do. But let's take this matrix and look at vectors in this special direction. Let's take this vector v1. It goes to this vector. How much of a stretch was there? The new vector is 5 times v1. Let's choose another vector, v2. That goes to this. That's also 5 times v2. It looks as if all vectors in this direction are stretched to 5 times their original size. And it so happens that every vector in this direction is stretched by a factor of 5. So the geometry of the situation is like this. For this particular matrix, we have a special direction, and every vector in that direction gets sent to a vector in the same direction, but 5 times its length. Well, let's now relate that back to the algebra of matrices.
Well, what's Norman just shown us? We saw that this matrix, acting on V1 in the special direction, gave us 5 times V1. And we saw this was true for another vector, V2 in the same direction. We got 5 times V2. In fact, for any vector x in that direction, we could get a scaling of 5 times x. But that's just for this matrix. We'd expect, in general, that for any matrix A with a special direction and a vector x in that direction, we'd get a constant stretching. It won't always be 5, of course. Let's call it lambda. So, that's what's going on. Ax equals lambda x. And that should be familiar to you. This equation is just a statement of the algebraic eigenvalue problem. So, if you solve this problem, you'll get eigenvectors, which are the vectors in the special direction, and eigenvalues, which correspond to the stretch factors.
So the geometric problem of finding these special directions is equivalent to an algebraic problem that you've met before, the algebraic eigenvalue problem. The special directions are just the directions of the eigenvectors of these matrices, and the stretch factor in each case is just the corresponding eigenvalue. And that gives us an algebraic reason for why we didn't get a special direction for this rotation matrix. You saw before the program that this matrix has got complex eigenvalues, and complex eigenvalues can't be interpreted geometrically in this way.
Hang on a minute. Before the program, you looked at this matrix as well. It's got 2 eigenvalues and 2 eigenvectors. And according to our algebra, there should be 2 special directions. You know about this special direction. This is the direction of the other eigenvector, and that should be special too. And it is, with a stretch factor of 2. But there's something rather different about this second direction. Before, vectors which were close to the special direction were moved closer still. But now look at what happens to vectors near this direction. This time, no matter how close you are to the second special direction, your vectors get moved further away. We can see that even more clearly in this way. Let's use the matrix on all of these vectors simultaneously. Clearly, there is a distinct movement towards the first eigenvector. In some sense, it's dominant. So, how can we explain this? Why is one direction more dominant than the other? Well, let's take a vector, any vector such as this one. What does the matrix do to it? We don't know offhand, but we do know what the matrix does to the eigenvectors. So let's split this vector up into the sum of these vectors along these special directions. So, what happens when we apply the matrix to this? This stretches 5 times. Let's stay here. And this one stretches twice. And that's to here. So, this starting vector is moved to the sum of these 2. And that's to here. And you can see that even though it was pulled in both directions, the pull was stronger here, 5, compared with 2 here. So the result was to move the vector closer to the dominant direction. And the dominant direction is just the one with the largest eigenvalue, the largest stretch factor.
So what Jen's just shown us is that if you apply the matrix to any vector here, it gets pulled 2.5 times more strongly in this direction than in this direction. So the result will be closer to this eigenvector. The vector sort of gets dragged round towards this dominant eigenvector by the matrix. Well, we've explored the geometry and we've found that the business of special directions is just a business of eigenvectors. But is it just an interesting piece of geometry, or is it any use to us? Well, in the rest of this program, we're going to look at the application of these ideas, and in particular, this idea of dominance. Now, what happens if you apply the matrix again? Then the result will be pulled even further around. So that if you applied the matrix repeatedly, eventually we might end up with an eigenvector. And that's the basis of an iterative method of calculating eigenvectors. So let's just look at that happening. We're using the same matrix, and we'll take an arbitrary vector to start with. One application of the matrix gives this. Now, the endpoint of the vector is off the screen. That's not a problem to us, but the growing size of these vectors could be a problem for a computer, because it means that the numbers in the calculation are getting larger. If they get too large, they could overflow the capacity of the computer. So we'll take a standard square, and after every multiplication, we'll rescale the result so that it lies on this square. The rescaling doesn't change the direction, just the size. Okay, so here's the next application. And the scaling, matrix, scale, and so on. And now we see that the vector's hardly moving, so we're close to the eigenvector. Start from the same place again, but now watch the scaling factor. Here we scale down by a factor of 11. Next time we scale down by a factor of 4.27, and that's closer to the eigenvalue. As the vector gets closer to the eigenvector, the scaling factor gets closer to the eigenvalue.
Now, all we're doing there is repeatedly multiplying a column vector by a matrix and then dividing by a number. That's an easy iterative numerical process that the computer is particularly suited to. And that process is the basis for one of the numerical methods in the computer package associated with this unit. It's a method we call direct iteration. Here's the computer all set up to go. Here's a statement of the data I've already entered. You see, here's the matrix, 3214. Here's the method, direct iteration. And I've input a starting vector. It can be almost anything. So, I can ask the computer to solve this. So, here's the printout. The computer multiplies this vector by this matrix to give us the vector 11, 7. It then divides through by the largest element, 11, to give us this vector. You can see that this vector has largest element 1, which in this case is exactly what we were doing geometrically on the square. And then we do this again for 17 steps. And you can see this vector tends towards what we know is the dominant eigenvector, and this scale factor tends towards the eigenvalue. So, our computer package produces the dominant eigenvector and the eigenvalue using only numerical methods.
Okay, let's just collect our thoughts for a moment. We've got a method of finding the dominant eigenvector, and it's called direct iteration. Jen's method took 17 iterations, which is quite quick. And in fact, the speed with which you converge to the solution will depend on the relative magnitudes of these eigenvalues. If this eigenvalue had been a lot bigger than this one, then it would have come round more quickly. If they'd have been more nearly equal, then the dragging effect would have been more balanced, and it would have taken longer for the vector to move round to the dominant eigenvector. And of course, if these eigenvalues had been exactly equal, then the dragging effect would have been exactly balanced, and you're in deep trouble. In a case like that, the package just won't work because you need other techniques. There's one other thing that I want to mention here, and that's what happens if one of your eigenvalues is negative. Well, supposing, for example, this one were negative, then this vector would successively be going backwards and forwards at each iteration because its sign would be changed. But nevertheless, it would still be converging in this direction. But there's a nice little payoff here, because the way the package works is to compensate for this behavior while it scales, so that this vector is always in this direction. If this vector flipped over, it would be scaled by a negative amount, so that we always approach this special direction from this side. But the computer detects this. It converges to the eigenvalue of largest modulus, but it gives you the sign as well. So you see, the dominant eigenvector isn't just the one with the largest eigenvalue. It's the one with the eigenvalue of largest numerical value. So, now you've got this eigenvector, but supposing that you wanted to calculate this other eigenvector, the one with the smaller eigenvalue. How would you go about that?
Well, before the program, you verified that the matrix A to the minus 1 has got the same eigenvectors as the matrix A. But whereas A has got eigenvalues 5 and 2, A to the minus 1 has eigenvalues a fifth and a half. So, for the inverse matrix, the larger eigenvalue corresponds to the other eigenvector. So, you could use direct iteration on the matrix A to the minus 1 to find the larger eigenvalue, a half, and that will correspond to the other eigenvector. Now, there's another method in the computer package which effectively does this for you. You don't have to feed in A to the minus 1. You feed in A and ask it to do the inverse iteration. And here you see the results. This converges to the eigenvector I want, and this scale factor converges not to 2, but to a half, which is the eigenvalue of the inverse matrix. And then, because we're using inverse iteration, the computer calculates what the eigenvalue of A would be, 2. So, inverse iteration will find for us the eigenvector whose eigenvalue has the smallest modulus.
So there's a method, in fact, two methods for finding eigenvectors and eigenvalues, provided that the eigenvalues are real or not equal. For the eigenvalue of largest modulus and its associated eigenvalue vector, we use the scheme here. We take a starting vector, apply the matrix A to it, get a new vector y dashed. Then we scale that vector and use that again for the next y, and repeat the process. And for the eigenvalue of smaller modulus, we use the same scheme, but based on the inverse matrix A minus 1. Okay, for a 2x2 matrix, that gives us all the eigenvalues. Although it's not the method one would usually use for a 2x2 matrix, there are other methods. It does give us a key to tackling bigger matrices. For example, we could try a 3x3 matrix, one like this. This matrix has 3 eigenvalues, minus 6.24, 7.43, 9.91. We used the computer package to calculate these. Iteration using A gave us the eigenvalue of largest modulus and its eigenvector, and iteration using A minus 1 gave us the eigenvalue of smallest modulus and its eigenvector. But how do we use the package to get this middle one? Well, we iterated using yet another matrix.
The matrix we used was A minus pi to the minus 1. Why did we choose that one? Well, this matrix has the same eigenvectors as A, and if lambda is an eigenvalue of A, then 1 over lambda minus p is an eigenvalue of this matrix. What happens if I iterate using this? I'll get the numerically largest value of 1 over lambda minus p, and from this we can calculate the numerically smallest value of lambda minus p, and this in turn gives us the value of lambda closest to p. So, for this matrix with these 3 eigenvalues, minus 6.24, 9.91, and between them 7.43, the behavior of the iteration depends on p. For any particular value of p, the iteration process will give the eigenvalue nearest to p. Here, it will give 9.91. Here, it will give 7.43, which is what we want. But if you don't know that middle eigenvalue is at 7.43, how can you choose a value of p that will do?
So we have an iteration scheme, but it depends on choosing a value of p that's closer to the eigenvalue we want than to any other eigenvalue. You see, we found the eigenvalue of smallest modulus, and what that tells us is that there can be no eigenvalue between minus 6.24 and plus 6.24. We've also found the eigenvalue of largest modulus, 9.91, so there can't be anything beyond there. So it's worth looking for eigenvalues between these two. If I choose a value of p, which is halfway between 6.24 and 9.91, then it'll be closer to any eigenvalue in that interval than to 6.24 or 9.91. And in fact, that's how we calculated 7.43. There could be a problem, of course. If there weren't an eigenvalue in there, then we would converge to either that one or that one. In that case, you do the same thing, but over here, and look for negative eigenvalues.
So, for this 3 by 3 matrix, I've run the package with p equal to 8, halfway between 6.24 and 9.91. And you can see that it converges. But this figure is the eigenvalue of a minus pi to the minus 1. So, we need to calculate the eigenvalue of a, which comes out, as expected, to 7.43.
So that's our process. It isn't the only process that's suitable for a computer. Remember that we have to do an iteration for each eigenvalue that we want to find. So in the next section of text, you'll study a method which gives all the eigenvalues as a result of one iteration. But now that we've studied eigenvalues, it prompts the question, is all of this worthwhile? Is this special property, this business of ax equals lambda x, just an interesting intellectual exercise? Or is it the mainstream of mathematics? Well, you'll see in the next unit that it's got important applications. In fact, in the very next television program, you'll see that in explaining why these two balls don't coincide in their first pass across the bowl, we're led naturally and directly to the eigenvectors of a matrix.